we can summarise my presentation today, slightly tongue-in-cheek, in 3 words. My clicker's not working. There we go. Knowledge is power, or slightly more mathematically, power is proportional to knowledge. In terms of control, the precision with which we can control a system is roughly proportional to the amount of information we have about the system. In terms of building automation, the more information we have about a building, the more precisely we can control it, the more efficiently we can maintain comfort conditions and reduce the amount of energy required to achieve that. The primary information that we need is split into 2 types: design information, thermal and other physical characteristics of the building, and topological information, the relationship between the primary energy sources, the energy distribution, and the actual environmental conditioning of the spaces which are fed by those systems. And then the operational information, measurements or predictions or estimates of parameters such as temperatures and indoor air quality values, and also temporal and spatial distribution of occupancy. When is the building occupied and where are the parts of the building that were occupied? So to begin with, we're going to look at a typical low information building. We have a building here with a wet heating system with radiators with mechanical TRVs attached to them. Somewhere there's a plant room with a primary heat source and heat distribution plant, and a building management system with sensors and actuators to control the plant. But outside of that, it's very common for there to be very little information about the actual spaces we're conditioning, which is being fed to the BMS. So in this example, we've got an outside air temperature sensor, which gives us an estimate of the steady state losses of the building, and therefore how much energy we need to put in to make up for those losses. And 1 or more inside air temperature sensors, which gives us an idea of the dynamic conditions. How much is the building cooled down? How much do we need to heat it? When do we need to switch the heating on? But of course, where we put that sensor, or those few sensors, is a big question, because where does one place one to be representative? So from the perspective of control, we have a feed-forward control system. We take global parameters, the outside and inside air temperatures, and some sort of occupancy profile. We use that to make a decision at a global level of when to run the boilers and when to run the heating circuits, because we do not have much information from the individual spaces we're conditioning to tell us any more detail. From the perspective of the heat distribution network, because we don't know where the heat demand is, it's necessary for us to distribute heat everywhere. So with a large building, we can have to heat up 10 or 20,000 litres of water from ambient up to 60 degrees, say, at startup, in order to distribute water to every radiator. And this type of control is effectively contingency-based control. We're generating heat on a contingency that somewhere a radiator may need to use it. And obviously, that is not a very efficient way to heat a building, particularly these days with greater diversity of occupancy, greater levels of unoccupancy. And so, recognising this, the latest Part L of the building regulations calls for buildings to be zoned, so that individual zones are monitored using sensors, and we control the zones using the actual measured activity in the rooms and temperature differentials, rather than simply relying on time schedules. The result of this is that we have, instead of a feed-forward control system, we had a feedback control system. We read the information from the zones and then make decisions at the distribution plant level and central plant level whether to run the plant and how to run the plant. And studies have shown that this sort of zonal control can achieve sort of 30% energy savings as opposed to global control. So let's take our building and add some more sensors. So for every occupied zone, we're going to add a temperature and a motion sensor. And we're going to replace the mechanical TRVs with smart TRVs, which gives us the ability to remotely adjust the set points of the TRVs. So for example, between a frost level, setback, occupied target temperatures. It gives us the ability to allow the users limited control, limited set point adjustment of the TRVs, and perhaps reset those set points every day so they don't leave them at 28, or even lock the TRVs so the system is purely controlled by the BMS and the users don't have any control. And finally, it gives us the ability to see the position of every single radiator valve in the building, which allows us to see where heating is required and how much heating is required. So suddenly we've got a huge amount more information. Look at the control system, we can turn the control on its head now. Instead of feed forward, we now feed back. We look at the individual control zones, we aggregate the requirements for those control zones, and we feed them back. And this allows us to make more intelligent decisions at heating circuit level and at, for example, floor zone valves. We can look at a floor and say, well, if I've got 30 zones and only one of them's asking for heat, do we send heat to it? Do we run the boilers? And this allows us to, it gives us a few more adjustments that we could put into the BMS, but fundamentally it allows us to aggregate backwards towards the boilers and only run the boilers when there is a demand. From the perspective of the heat network, we now have a dynamically reconfigurable heat network where the much smaller volume of water is heated, and we only effectively route water to those zones where there is a heating requirement. So very different picture from the one where we're sending water everywhere in case it's required. Of course, all of that information is not free. So putting in sensors has a cost associated with it, and obviously any energy savings we achieve needs to be justifiable from the capital cost. So in BMS terms, there is a very common metric, which I'm sure some of you are familiar with, the point count, which is the number of inputs and outputs in the control system. If we look at the cost of that point count, how much it costs for the hardware and the installation, and divide it by the point count, we get a notional value, which is the point cost. How much does it cost to put a room sensor, for example, in a space and make that data available to the BMS? So we've got a room sensor in here somewhere. It probably costs about £10. But to actually make that data point visible in the BMS can cost several orders of magnitude. So the cost of a wired point involves the cost of the BMS hardware itself, the input-output hardware, the real estate in the control panel, the cost of wiring the control panel, all of the electrical installation associated with running the cabling back to the BMS and actually commissioning it, proving that that sensor is actually the one we see in the BMS. And that cost can be £500 to £800 per point. And I personally think that it's easy to find installations where it's more than £1,000. So a £10 sensor, but £1,000 installation cost means we've got a huge infrastructure cost. And if we're looking at sort of any sort of cost-benefit analysis, we don't have to think too hard or do any detailed analysis to realise that putting in hundreds of sensors is not going to be justifiable as far as the payback is concerned. So one of the obvious things to do is say, well, if our infrastructure cost is so high, let's get rid of the infrastructure. And so therefore one of the potential solutions is to go wireless. So wireless controls have been used in BMS for several decades, but generally never with great success, mainly due to the radio range of the devices and the battery life. But in the latest generation of IoT, we're seeing a new emergence of much more efficient devices that can transmit over much greater distances in buildings and have battery lives, in some cases, that last 10 years, last for the lifetime of the device. And also have much better security, because obviously that's a big concern these days. And the result of that is that the infrastructure cost is actually a very small fraction of the cost of the sensor. So if you have one wireless access point, for example, the more sensors you add to that access point, the cost of the infrastructure gets spread across the points, and it can be only a few % of the cost of the sensor. So, and the result of this is we have installed sensors where individual total installed cost of a sensor could be £70. And in fact, a lot of these sensors are multi-point sensors. So for example, the sensors we use in occupied spaces measure temperature, humidity and motion. So theoretically that's 3 points. So you could say that the point cost is around £25 per point, which is obviously a lot better than £1,000 per point. So the technology we've selected for our applications is LoRaWAN, which some of you may have heard of, which demonstrates great penetration of buildings and long battery lives. But probably the most compelling feature is that there is a huge catalogue of products available at the moment, and it's growing rapidly, of all the types of devices we would want to use in BMS. So temperature, motion, CO2, lots of air quality sensors, remote relays, remote TRVs, and metering. Effectively all the things in the BMS which are really hard to get to because you've got to run long wires out of the plant room to get to them. So we have, using the ideas here about occupant-driven control and wireless sensors, implemented a BMS solution which combines conventional wired BMS control with the support for thousands potentially of wireless field controls, and implements occupant zonal control, demand control, allowing us to create hundreds and hundreds of control zones, so individual cellular offices, for example. We also capture, or have created software tools which allow us to capture the topology of the building, so we can construct a relationship between the radiators, the heating circuits they're attached to, and then the boilers, which allows us to create demand trees. So we can aggregate the demand for a set of rooms and then make decisions about whether we feed that area using zone valves, or whether we actually run a heating circuit using the pumps in the plant room, or whether, in the end, we run the boilers or not. I think that's it. So I've got two examples. I'm going to skip through this one very quickly because I've only got a few minutes left. We've deployed this in a number of sites, different types of applications. One is a set of care homes owned by Portsmouth City Council, which are gas boilers, residential self-contained flats. And we installed about 950 wireless TRVs across 6 sites. And with those, controlled the sites and used demand feedback to determine boiler operation for heating purposes, and measured an overall gas reduction of 25%, which was quite pleasing. That included hot water energy, so if we just look at the gas energy used by heating, we achieved a reduction in the heating energy input of around 36%, which is very pleasing. Second example is Somerset House in London, which is a Grade 1 listed 18th century Georgian building, with CHP and boilers providing heating to 6 VT circuits which feed 350 cellular offices and various corridors, WCs, etc. And you can see the wings that we fitted the controls to. So we fitted around 750 wireless TRVs and 350 room sensors with temperature and motion into these 3 wings, which are each 6 stories high. And it's an interesting application for a number of reasons. One of them being, as a heritage building with Grade 1 listing, it's very, very difficult to do any wiring around the building. And so it's a good demonstration of how wireless controls can be used in the field in these sort of applications. And it's also a good demonstration of wireless control anyway, because this building structure has got incredibly thick walls. So it's a good road test of wireless devices in general to demonstrate how they can be used in challenging scenarios. So I think I covered all of that. And this is an example of actually wireless coverage. So the orange dots are 2 wireless access points. And the floor plan there is of one of the wings. So with 2 access points, not only did we successfully get coverage of the entire wing, but also the floor below and above this floor. So overall, over those 3 wings, we only had 18 wireless access points covering 1,200 wireless devices. So infrastructure cost-wise, very, very small compared to the total amount of field controls. So having analysed the data for a couple of years, we've demonstrated a reduction of around 30% in the gas boiler energy being put into the system, which just measured in kilowatt hours the energy manager was very pleased because it was 1 million kilowatt hours that we reduced their bill by, which was quite significant. So, conclusions. I mean, fundamentally, the conclusion is by putting in more intelligent controls, provided they're justifiable cost-wise, we can achieve energy savings. But I think the two conclusions I think we learnt from doing these sort of projects is that when you're deploying thousands of controls, field controls, you need software tools in order to capture all of that information and commission it efficiently. And the second thing is smart buildings, to coin a phrase, require smart maintenance. And when we're looking at things, particularly where we're interacting with a mechanical system with smart TRVs, who maintains them? Because your average maintenance contractor with his favourite weapon is a spanner is not maintaining these devices properly. You know, we're putting very, very intelligent controls in all sorts of equipments in a building, but if it's commissioned and made very energy efficient, for the rest of its life it has to be that energy efficient, otherwise it doesn't control it. But a standard mechanical contractor is much more likely to not maintain these devices correctly and result in us losing all of the efficiency once it's handed over. So I think there's a lot of requirements for either controls contractors to get much more involved in this, in the maintenance side of things, or maintenance contractors to have much more intelligent skill sets in their teams that can maintain these sort of smart controls. And that is it. Thank you very much.